What I want to do here is give you a couple of examples of questions relating to number bases and converting numbers from base 10 into different bases and vice versa. So I'm going to put up 6 questions for you, pause the video and have a go at them, and then I want you to come back and check what you've done against the working I present. So here you go, there are your 6 questions, pause the video and have a crack at them. So, first question here was I want to convert each of the following from the given base into base 10. So doing this, we have to remember what we're doing is we're looking at increasing powers of the base number, how each digit in the original number, so in the first case the 415, relate to the positioning of these, and then combining them all together. So we know we're after base 4 here, and we've got 3 digits. So I'm going to set up a table with 4 to the power of 0, 4 to the power of 1, and 4 squared. And in here, what I'm going to do is I'm going to place the digits 4, 1, and 5. So what this tells me is then to turn it into base 10, what I'm going to do is I'm going to do 4 times 4 squared, plus 1 times 4 to the power of 1, plus 5 times 4 to the power of 0. And I'm just going to do this calculation, get each of these numbers, and combine them and add them together. So doing each of these, what I end up getting is I get 64 plus 4 plus 5, and that there then gives me a solution of 73. So this number here, 415 to the base 4, is actually 73 to the base 10, so what we would normally use in our number system every day, it represents the number 73. The second example was the number 9710 to the base 6. Now, again, similar approach to the other one. We set up our table with our bases in ascending powers. Now this time, we've got 4 digits, so we have to go all the way up from 6 to the power of 0 to 6 to the power of 3. What we then do is we insert our digits in the appropriate columns, so the 9, the 7, the 1, and the 0, and we use this to then essentially get the elements that we want. So what it's telling me is I want 9 of the 6 to the power of 3s, plus 7 of the 6 squares, plus 1 of the 6 to the power of 1s, plus 0 of the 6 to the power of 0s. So we know what we're bringing together, we know what we're after, calculate each of these, and then combine it all together. So if I do each of these bits of maths, what I'll end up with is 1944 plus 252 plus 6, and then all I do, add them all together, combine it, and bring it together, and I get 2202. So the number 9710 to the base 6 represents the number 2202 in our base 10 number system. The third example I gave here was I wanted to convert this from base 12 into base 10. Now remember we said if the base goes beyond 9 and we use letters, these represent numbers from 10, which we'll let A represent, all the way up. So in this case, I want A32G to the base 12, and I want to know what that represents. So again, we've got 4 digits, so when we set up our table, we're going to set it up in ascending powers of 12, in 4 columns, starting from 12 to the power of 0, going all the way up to 12 cubed. What I then do is I look at this and I start to insert the digits into the places they need to go. Now, easy ones to do are the 3 and the 2. They're right in the middle. What I need to do is figure out what numbers and what digits the A and the G represent. Well, the A represents 10, and if I equate up the alphabet and the numbers, the G represents 16. So what that then means is I'm going to be doing 10 of the 12 cubes, plus 3 of the 12 squareds, plus 2 of the 12 to the power of 1s, plus 16 of the 12 to the power of 0s. Now that I'm at this stage again, it's just a case of calculating numbers, combine it all together, see what we got. So doing each part of them there, so the first part there, the 10 times 12 to the power of 3, gives me 17,280. Plus then the second part, 3 times 12 to the power of 2, gives me 147. Then 2 times 12 to the 1 gives me 24. And then 16 times 12 to the 0 just gives me 16. So now I've got all the parts, combine it all together, what I end up with, 17,467. So that there, A32G to the base 12, represents the number 17,467 in our base 10 number system. So converting from a given base into a base 10 follows this technique every single time. Now if I wanted to convert each of the following numbers from our base 10 system into the given base, remember we approach this similarly to the Euclidean algorithm. The rule that we have is the remainder doesn't matter, so if the remainder is 0, we still keep going. It's the quotient that matters. When the quotient is 0, that's when we stop. So if I'm going to look at the number 30, I'm going to put it into base 2. I start by saying, fine, 30 is going to equal something times 2 plus a remainder. Well, we know 30 is 15 times 2, and there's a remainder of 0. We then keep going, so our quotient was 15. So 15 in this case is going to equal 7 times 2 plus a remainder of 1. Keep going another step, our quotient is not 0. So 7 is equal to 3 times 2, again plus a remainder of 1. Keep going. 3 is going to equal 1 times the 2 plus a remainder of 1. And we're nearly there because our last line is going to start with 1 equals. And at this stage we could say, right, well it's a fair bet to say that 1 is equal to, a quotient is 0. So 0 times 2 plus a remainder of 1. So now that we have the quotient equal to 0, we can stop. And then we read from the bottom, going up that way, and that's our number in the new base. So the number 30 in the base 10 is equal to 11110 to the base 2. That there represents 30. And if we follow the techniques that we did previously, converting a number from the given base into base 10, what we'll find is we get back to 30. The second one was converting the number 53,467 into what we called octal form, so base 8. Follows the same set of steps, similar again to the Euclidean algorithm, with that same rule. Once the quotient is 0, that's when we stop. So we start by saying 53,467 is equal to, now remember we're after something times 8, because 8 is the base number we're looking at, that's what we're looking for. Well, in this case, it's 6,683 times 8, and I've got a remainder of 3 from that calculation. So then, we keep going. So 6,683 is going to equal, again, something times 8. So in this case, it's 835 times 8. Then add on my remainder, which in this case, again, is 3. We then go to our next step. Our quotient still isn't 0. So we still have to keep going. So 835, something times 8, well, that's 104. So it's going to be 104 times 8 plus a remainder. Now again, in this case, the remainder happens to be 3. It's purely coincidental that all the remainders are 3 in this case. There's no given rule that they will all be the same. It just happens to be. We then look at the next step, which is the 104. So 104 is going to equal something times 8 plus a remainder. Well, 104 is equal to 13 times 8 exactly. So it's going to be 13 times 8 plus a remainder of 0. We keep going. Remember, remainder being 0 doesn't matter in this case. It's the quotient. Quotient's still 13. It's still non-zero. We have to go again. So in this case, we know 13 is going to equal 1 times 8 plus a remainder of 5. Now we're at a stage where we could say, next line, because the quotient here is 1, we're going to end up with a quotient of 0. So we can say 1 is equal to 0 times 8 plus a 1 there. Now my quotient here is 0. That's great. Bottom to top, reading from that way, gives me my new number in the order we want. So in this case, it's 150,333 to the base 8. That there is 53,467 in octal form. And again, if we follow the steps of the previous set of examples, going from a different base into base 10, we'll end up back to the number 53,467. Last example I gave was the number 697 as a base 7 number. Again, Euclidean algorithm style movements. So we start by saying 697 in the proper form that we want. So something times 7 plus a remainder. So in this case, 697 is equal to 99 times 7 plus a remainder of 4. Quotient's non-zero, we keep going. So 99 equals something times 7, so in this case it's 14 times 7, plus a remainder of 1. Again, non-zero, we keep going. We have 14, well that's equal to 2 times 7 exactly, plus a remainder is 0. Fine. Remember, it's not the remainder being 0, it's the quotient being 0. That's what we're after, that's the key thing. Quotient here is 2, so we've got another line. 2, well that's going to equal 0 times 7 plus a remainder of 2. Now the previous examples always started that last line with 1 equals. You've got to remember, it's not always going to be 1 equals. We could end up with 2 equals in this case. We could end up with other numbers on that last line. The key thing is 0 times the base number plus the remainder. That's the key thing. That's 0 times. The quotient is 0. Then we read going up the way. So in this case, it's 2014 to the base 7. That number there, the 2014 to the base 7, converting it back to the base 10 system, again like we did previously, that'll give me an answer of 697. That's what it will represent in our number system. Converting between number bases is a fairly simple standard process that follows the same set of steps. Converting from a non-10 base system into a base 10 system follows the same set of steps and guidelines as we did previously, representing the base powers and then where each of the digits lie, and then combining it all, and then going from a base 10 number system into a different base follows this set of steps here, again similar to the Euclidean algorithm. The key rule here is it's not the remainder being 0 we're after, it's the quotient being 0. Remember, remainder being 0 with the Euclidean algorithm was looking for the greatest common divisor. Here, we want the quotient being equal to 0, so that we've then got a representation in a different number base of our original number from the base 10 system.